Hello, we are Team 7, and we welcome you to our presentation of our Interim stapler project. We chose the Boston stand-up stapler for our product. Our primary customer base is office and school workers who need a stand-up stapler with a low storage profile. Our secondary customer base is advertisers and extracurricular groups who are aiming to staple things onto walls without caring about stapling individual sheets of paper together, and we estimate an annual production volume of 125,000 units. Here is shown the CAD for our primary module designed for the main use of office workers, and the secondary module designed for use mainly in stapling to walls. Note that the secondary module has removed the lower jaw so it's more convenient for people to be stapling onto a wall, and also reduces the total cost of this module.
Here we have an exploded view of the CAD for our primary customer. We have 18 unique parts, 2 of which are fasteners. So the first assembly option that we considered is highly parallel. We have 4 initial parallel assemblies: the top cover assembly, staple guide assembly, staple cartridge lower assembly, and lower assembly. These are all then brought together to form the staple cartridge base assembly and then put into the complete stapler. Our second assembly format follows a more linear assembly process, with a primary starting base of the bottom cover and lower assembly, in which a staple cartridge assembly is then added. From here, there's a more linear assembly, adding the staple upper guide and pivot pin to form a functional staple cartridge, and then allowing for the sliding mechanism by linearly adding the locking pin staple slide and long slide spring. Finally, the top cover is added to create a functional stapler. When comparing the two assemblies, we can see the advantages of having a large number of parallel assemblies, which allow for a high level of individual part accessibility and an ease of performing multiple assemblies at the same time, resulting in a lower total assembly time and therefore a lower total assembly cost. For these reasons, we have selected Assembly 1 as our primary assembly method based on these metrics here: ease of transferring and handling parts, ease of locating parts, ease of fastening and joining, ease of testing assemblies for their function, and ease of assembling subassemblies in parallel.
For our function analysis system technique table, our task function is binding materials, and our primal basic functions are housing, dispensing, and securing staples. These branch into basic functions of apply force, access housing, separate staple, feed staple, position staple, and form ends, as shown on the figure. Special features of our stapler create supporting functions of increasing grip and reducing footprint to assure convenience and enhance the product. Additionally, it is of note that many steps in the binding materials process are performed by the user, such as loading the staples and adding the material. Our function component mapping matrix uses the subassemblies of assembly diagram 1 in the first column and the basic functions from the previous slide in the top row. Each function corresponds to a part and has less than 40% of the overall parts.
The bill of materials includes 16 unique parts and 2 screw types for the entire assembly. This includes part names, material type, part dimensions, quantity, and part cost. Costs for the plastic components are verified using custompart.net estimations, along with other factors within manufacturing. All sheet metal and spring components were estimated by material costs and factoring other manufacturing costs. Screws were estimated using McMaster values for similar screw types. The injection molded components tend to be the most expensive, with sheet metal and springs following. The total cost came in at $12.44, which is within the 50 to 70% material cost out of the $20 item. Quad charts are displayed for the individual parts. The top and bottom cover can be seen to have high cost but low functional importance. Moving into pivot pin and some of the sheet metal components, the parts cost falls off, but they do tend to have a higher importance to the assembly's function. The high importance and lower cost trend continues with the rest of the sheet metal components within the main staple compartment, although the nose plate and staple bend plate have low functional importance since they're independent of the main function. The springs tend to have lower importance and cost besides the long spring used in the staple mechanism. Assembly screws provide low importance and cost, as they could be replaced by other means of attachment.
Here is the functional differentiation table, which describes the similarities and differences of the product functions. With our two products, most functions are the same for both customer groups, with the only difference being the form ends function, as they staple different materials and have different needs. Here is the component commonality table, which describes the similarities and differences of the product's components. With our two products, most parts are the same, with the differences being the top cover, parts creating the lower jaw, and additional spacers in the secondary product.
Shown here is our product family assembly diagram. The stapler cartridge assembly shown in the top left corner is consistent in both the primary and secondary customer assemblies, and then the lower assembly is only present in the primary customer assembly, and then after that it is differentiated the rest of the way through, shown in the bottom figure, as the top cover is different in both assemblies.